Jusqu'à présent, nous avons vu comment
Up
se
to
forment
now, we have seen how are formed celestial bodies that compose the universe, how they evolve, and what are the physical phenomenons which give them their mass and luminosity. But what for the universe as a whole? What's its origin? How does it evolve with time? What will become of it? What is its global composition? All these questions are closely linked and belong to the field of cosmology. The theory, which currently best explains all observations that are at our disposal, is the Big Bang theory, where the universe was born of one initial explosion, some 13 to 8 billion years ago, followed by an extremely rapid expansion, called inflation. Then, a slower expansion, as was found in 2030s. Since the years 2000, we know that this expansion is accelerated, but the reason for this remains completely unknown. This can be explained only by invoking the existence of a repulsive force due to some unknown form of energy called dark energy, and that would counteract the gravitational force, which tends to make the universe contract itself. So we said that the universe is expanding. That doesn't mean that the universe was born in one point and is expanding like a spherical ball, but it means that all points are growing further apart from each other with some factor called the expansion factor. So for example, here, we have a certain distance which becomes longer as the universe is growing. We have another distance here, which also becomes longer by a certain factor, etc., etc. And the same for the distance here. And if we call r the distance here, and r the distance here between 2 points, we have r equals a times r, where a is what we call the expansion factor. So let's look at this expansion factor in more details. So here we have a grid representing the metric, defining how we measure coordinates in the universe. And this grid will evolve with time. So time flows like this. And we can localize objects on this grid in various ways. For example, we put an origin here. So the origin will be here, at an instant t later. We take an object at a coordinate x, and then we let the system evolve with time. The x-coordinate hasn't changed. For example, we take a section here and a section there to go to x, and we take a section here, a section there to go to x. So x is what we call the co-mobile coordinate, which moves with the reference grid. We can also localize objects in a different way. We can say that the distance from 0 and x is the distance r, which is here. So r, t. And then, a moment later, the distance rt has grown. So this rt will be equal to a certain expansion factor times the co-mobile coordinate. So a t is the expansion factor of the universe. Now we will see how all this evolves. So, as we said, rt is equal to t times x. Of course, we can also write that x equals rt divided by at. Then, if we derive the expression to get the velocity, we will try here to recover Hubble's law. We will have here dA divided by dt times x, because x doesn't change with time. So if we input x here, we will have that r, that is v, rt, will be equal to a t divided by a. I just introduced x here, times r. And what we will do here, we will write that this is h, and this is the expansion rate of the universe. So we had an expansion factor, a, while this is the ratio a divided by a. That is an expansion rate. So now we can also write that v, r0, t0, is equal to h, t0, times r, t0. In other words, we have here Hubble's law. Namely, v equals h0 times r. That is to say, times the distance that separates us from an object. So what we wrote here is nothing other than Hubble's law. Then, this Hubble expansion law we will write again here. V equals h0 times d. That was Hubble in 1929. But actually, the idea was also proposed by Georges Lemaitre, a Belgian astrophysicist, in 1927. Drawing this law, as we have already seen, it connects the distance, long distances indeed, measured in megaparsecs, MPC, to the velocity, also large velocities, measured in kilometers per second, km divided by s. That is what we call the recession velocity of galaxies. And we have a linear law between velocity and distance. And what h0 measures is the slope of this line. The present value of h0 isn't very well known. To date, there is a 10% error margin on the exact value, perhaps a bit better in the more optimistic cases. It amounts to 70 kilometers per second, MPC. Right, these units may seem strange, but they are indeed kilometers per second, per MPC, that are measured. Now, the units can be simplified. The true dimension of h0 is in fact the inverse of a time. Thus, I divided by h0 belongs, of course, to the time dimension, and is actually the age of the universe. So why? Because if we know the distance and the velocity of a point, we can find the time needed for that point to be in contact with us. So, we have an expanding universe. All points were in contact at the beginning, at the Big Bang. And 1 divided by h0 later, 13.8 billion years later, the universe has its present shape, its present size. So we have an expanding universe. Now, what is the link with what is called the redshift, the cosmological redshift? We can write the Doppler effect, namely the ratio d. This is observed minus emitted divided by emitted, which is equal to dV divided by c. That is the Doppler effect that we have seen in chapter 3.2. Now that we have seen that following Hubble's law, that v equals h times distance. So here, we have a differential. Hence, we also have a differential there. We have a constant c which stays here. H, as we said, is a divided by a. And we have dr divided by c, which stays here. Now, a certain time, dt, is needed to travel the distance dr with the velocity c. So we could write that as a divided by a times dt. Now, what does that mean? Rearranging these two terms here, it means that d is equal, remembering that a is dA divided by dt, and then we have dt divided by a left. So in the end, we obtain d equals dA divided by a. This is a differential equation of the first order. The solution to this is a equals a certain constant k times a. Thus, at the present epoch, we have a equals 1. So we have that emitted 1 is equal to observed. Because at present, the wavelength, with an expansion factor of 1, the emission and observation wavelengths are the same. So we have a equals 1 here, and this implies that the constant k is equal to observed. This is simply the Doppler effect for a universe with an expansion factor of 1. Now, if we rearrange the results here, what we will get is that OBS divided by emit is equal to 1 divided by a. It is exactly this equation once we have replaced the k constant by OBS. We also have the Doppler effect formula, telling us that OBS minus emit divided by emit is equal to v divided by c, as we have seen, and we will set this as being equal to z, and this will be, by definition, the famous redshift. Now, if we gather these two equations, we will see that we will have OBS divided by emit equals 1 divided by a, namely the inverse of the expansion factor, but it is also equal to 1 plus z. This implies that, if we want to know the redshift of an object, we measure a given observed wavelength. Let us take, for example, a line in a spectrum. If we know its wavelength at rest, in other words, the emission wavelength, the intrinsic wavelength of the line, then we can find a redshift z. That is the well-known equation of the cosmological Doppler effect. Now, for example, let's take the Hubble Deep Field, as we did several times before in this class. We see that there are many galaxies of all colors. Some are blue, others are rather green. Yet others are red, like here, and there are two reasons for that. First of all, galaxies have intrinsic colors. Some have blue and hot stars, just born. Some galaxies have an intrinsic blue color. Others will have, for example, a lot of dust making their color redder, or contain a population of old stars with low masses. So there are multiple reasons for the observed colors of galaxies. But one additional reason is the cosmological redshift. For that we can draw the spectrum of a galaxy in a schematic way. So a galaxy spectrum resembles this. There are stars in a galaxy. So we will have the break at 4,000 angsters ms, Balmer's break, that we had already seen in the chapter dedicated to hydrogen. So here, we have a typical feature at 4,000 angstroms, if the galaxy is at rest, without any cosmological redshift. Now this is the wavelength of emissions when at rest, and observed will be equal to 1 plus z times emitted. So if we have an object with a very high redshift, 5 for example, we will multiply 4,000 by 5 plus 1, or 6. So we will have wavelengths that will move like this, far into the red. I will put here again the wavelength, and there the flux, since we have a spectrum. So we will multiply the whole spectrum by that factor, 1 plus z. So we will find here again the break. That was seen before at rest, but now 1 plus z times faster. And the spectrum will be stretched by a factor 1 plus z. So everything is stretched by a factor 1 plus z in cosmology. So now, if I add filters to this, for example, a filter here, and a filter there, and one here, and then I integrate the light, as we did before in the first chapters of this course, I will have a lot of flux here, in an infrared filter, for example. Here, considering the red filter, I will have a moderate flux, and then almost no flux at all in the blue. Now, if we make a true color image of a galaxy with the spectral distribution, we will have typically a galaxy, as we can see here, which will appear very red in a true color image. Of course, all intermediate situations occur. In images like these, you can find galaxies without any colors. First, because they have an intrinsic color, and second, because they have a certain cosmological redshift. Remember, the universe is expanding, and a very simple way to determine whether it will expand forever or not is to see whether the system is bound or not. I mean the universe as a whole. So, is the universe bound or not? Is it a gravitationally bound system? So we write the equilibrium between the kinetic energy and the potential energy. Here, m is the mass of the universe. R is the radius, or characteristic radius, v the velocity, of a test particle in the universe. This is 0, so it would be the total energy of the universe. Now we have seen that v is h0r, namely h0 times a distance, squared here. We move the 2 to the other side of the equation, thus obtaining 2gm divided by r. And this, if we assume a constant density, will equal 2g divided by r times 4 divided by 3, r. This allows us to define a density, which can be defined as a critical density, the value of which is 3 divided by h0 divided by g. So this is what we call the critical density of the universe. It is such that, if it's larger than critical, then the potential energy is larger than the kinetic one, and we have a contraction, or at least a fading expansion. And if it's smaller than critical, then we have an everlasting expansion. So we can see that the density of the universe is of crucial and far-reaching importance regarding the future of the universe. For that reason, it is extremely important to understand the energy balance, the different density contributions of the different components of our universe. Currently, the very fact that the universe is undergoing accelerated expansion implies, within the framework of the Big Bang model, that we have 68% of dark energy. That is the energy balance of the universe. This dark energy is repulsive and explains or mimics a universe undergoing accelerated expansion. On the other hand, we have 20% of dark matter, which is subject to gravity, and as such, tends to make the universe contract. And the proportions we have here result in a universe in accelerated expansion. And then we have a very small fraction of the total energy content, 5%, which is normal matter, called baryonic matter. So this baryonic matter includes the proton and neutrons, and by extensions of electrons that are not baryons but actually leptons, but are associated with normal matter, which is called normal or baryonic. Some of this matter, which emits radiation, is in fact the subject of all this course. So normal matter. But that doesn't emit light or light at the wavelengths we can observe. And then there is also dark matter that does not emit any light at all, at any wavelength. We have no idea of what it is. So if we talk about dark matter, it can't be two things. Either dark matter, here of which we have absolutely no idea, or normal baryonic matter, which we cannot see, because either it doesn't emit enough light, or it emits at wavelengths we do not observe. So now, these 5% of baryonic light has a mass distribution as follows. 5% of normal baryonic matter, which are composed 80% of gas, only 20% of stars, and 0.1% of dust. You remember these dark lines that absorb the light in galaxies and dark holes, even if they are very compact objects. There are very few of them and represent only 0.01% of the energy or the mass. So these numbers are taken from observations of the cosmic microwave background, CMB, radiation. What is it all about? First of all, it's a black body radiation, whose temperature is 2,728 degrees Kelvin. And there are small spatial variations of temperature of around 10 to the power of -5. Now, if we take the mean temperature over the whole sky, we will find a perfect black body, which is represented by this curve here, measured by the COBE satellites, which stands for the Cosmic Background Explorer. It's an American satellite from NASA, which has measured for the first time the temperature of a cosmological background. So the blackbody radiation is a radiation at 2,728 Kelvin. We measure the temperature of the sky background everywhere, in all directions of the universe, isotropically, equals to 2,728 degrees Kelvin, with small variations of 10⁻⁵. At the beginning, just after the Big Bang, the universe had a much larger temperature. Temperatures, of course, that cooled down due to the expansion. And at the present time, the temperature is 2,728 degrees Kelvin. So, what is the history behind the discovery of the cosmological background? First of all, come the first observations by Penzias and Wilson, who observed with a telecommunication antenna at a wavelength of 1,063 millimeter. So in the microwaves, they observed in different directions on the sky, and each time observed a background noise corresponding to a blackbody radiation at 2,728 degrees Kelvin. So they observed with an antenna that didn't permit them to construct a map of the sky, but they observed that wherever they did the measurement on the sky background, if they observed here, or anywhere, they were measuring 2,728 degrees Kelvin. So these maps that we see often, represented like this in an oval shape, they are the galactic coordinates. So we have here the galactic longitude and latitude we already saw in the chapter about the Oort constants. We have the whole sky map here, as seen by the antenna of Penzias and Wilson, then seen by the COBE satellite. It's the Cosmic Background Explorer, which measured and obtained the first sky map in 1992. What you see here is the millimeter image of the Milky Way. By improving the observations with the Wilkinson microwave background anisotropy probe, we can see more and more details in the map of the cosmological background radiation. There are still around 30 years each observation. So this cosmological background radiation is not observed easily. The observation of Penzias and Wilson is a constant over the whole of the sky, but we will have to take into account that the Milky Way is moving in the sky, and so we go towards a point that can be found here. Of course, if we look in the direction opposite to the movement, we find ourselves here, and we see a bluer sky, a bluer wavelength, in the direction of the motion, and redder in the opposite direction, due to the Doppler effect. So what we see here is what we call the cosmological dipole, because there are two poles like this, and this is simply due to the movement of the Milky Way with respect to the cosmological background radiation. Now, the velocity of the Milky Way with respect to the cosmological background radiation, measured through the Doppler dipole, is v equals 627.22 kilometers per second. Thanks to the Doppler effect, we have some sort of absolute referential here that allows us to measure the proper motion of the Milky Way in the universe. So now if we subtract this Doppler effect, we finally obtain the map of the cosmological background radiation, with also here the image of the Milky Way. The cosmological information is of course hidden by the Milky Way, but the Milky Way can be removed thanks to multi-frequency maps, obtained here with the Planck satellite, which is the last satellite to have taken CMB measurements. So this is recent, 2013 to 2014. By taking multi-frequency maps of the sky, we can, thanks to the apparent change of the Milky Way shape, subtract it to get the final image, which is here. So this is the map obtained by the Planck satellite. It's a temperature map, of course. The average of the temperatures is 2,728 degrees Kelvin, and there are small fluctuations around it. So these red points here are slightly hotter than this, and the blue points slightly colder, with variations of temperatures that are T divided by T, as we have already said, around 10 to the power of minus 5. The cosmological information is contained, in fact, in the statistical distribution of these small points, and this is what we want to measure very precisely at small scales, but also at large scales, because this is what the Big Bang theory predicts. So we will try to make observations that we will confront to the theory. Or in other words, we will confront the theory to the observations. So what is the cause of the fluctuations? When the universe was born, it was extremely hot. Then the temperature decreased, and while the universe was younger than 380,000 ans, we had a hot plasma, so hot that photons and electrons were separated. The gas was totally ionized, so now the photons present in the gas at that time were constantly in interaction with the electrons. They were, in fact, all the time scattered by electrons, until the moment where, due to the increasing temperature of the universe, because of the expansion, so when T diminishes, this intervenes at a time T equals 380,000 years after the Big Bang. So at that moment, we have what the recombination between protons and electrons. So now, if protons and electrons recombine, this produces hydrogen, with the consequence that photons cannot anymore be scattered by electrons. So photons propagate straight through a universe that is completely transparent to light and reach us. So what we see here is what we call the surface of last diffusion, or last scattering. The last time photons and electrons could interact with each other before the electrons recombined with protons. And it is for that reason that we say that the millimeter map, the microwave map of the sky, is the map of the cosmological background radiation, also known as fossil radiation, because it bears the imprints of temperature fluctuations. And so the density of the universe, as they were only 380,000 years after the Big Bang, the best description of the world in which we live, is provided by the Big Bang Theory. Far from being perfect, it still explains a large number of concrete observational facts, like the expansion of the universe, but also the cosmological background temperature and the spatial fluctuations throughout the sky. Still, to date, the accelerated expansion of the universe is 68% dark energy and 20% dark matter. We still cannot find a fully satisfying explanation. The solution of the problem will be found through the characterization of large-scale structures, and so by multi-wavelength observations of the whole sky. That has been done here by the Planck satellite, in the microwave wavelengths, to see the cosmological background radiation, but the sky will soon be mapped in optical and the infrared by ESA Euclid satellite and by ground-based telescopes.